He's received his bachelor degree in science in chemical engineering from Drexel University and his doctor of philosophy from the Georgia Institute of Technology School of Chemical Engineering. He currently is the vice president of science at Micromeritics Instrument Corporation, and his current research interests include advancing the comprehensive characterization of porous materials and catalysts using absorption and porosimetry. During his tenure at Micromeritics, he also served as the laboratory director. And today he's going to give us a talk about the absorption trends in the global market. And we're very happy to have you, Professor Dr. Jeff Kenvin, and we're very happy that Micromeritics is collaborating with us and looking forward to hear your presentation. Thank you very much.
Thank you very much. It's really a pleasure to have the chance to be with you today. These are topics that we love to discuss, and we really love to discuss them with the global community on adsorption. It's one of these areas in adsorption that we see that continues to get more and more significant over time. When we look around, who's really driving what's happening in adsorption right now? And I always put it into two categories of what's really significant. Let me see. Okay, very good. I always say M&A, and for the business people, that's mergers and acquisitions, but for science, it's materials and applications. And it's very motivating, particularly in adsorption, when we look at why things change for adsorption and why we think about things in new and better ways. Materials tend to probably be the strongest driver, and it comes from the creativity of all the researchers that are out there, because they look at different applications and they think of new materials that can solve those problems or be used in new implications. The strongest drivers recently have been new chemistries, so things like metal organic frameworks, ultra microporous materials, of course, zeolites, modifications of zeolites, moving to hierarchical materials to improve various performance of the materials, have really changed the way we think about characterization and the applications. Environmental and energy are really driving the application space right now. For the past, I would say, 24 months or so, we've really thought about, people have talked about quite a bit, CO2 capture and CO2 valorization. Okay, so, there's a great focus across the globe that we've got to take better care of our planet, and we've got to be very conscious of what's happening with the temperature of our planet. So the CO2 piece of things we've seen coming for, I would say probably more than a decade on the research side and new material side. But now it has global focus for all people. And people you talk to now acknowledge that there's a significant problem that we need to solve. Of course, on the energy side, there's also a renewed interest in hydrogen, of course, and energy storage applications, so batteries. It's very difficult to turn on the news and not see people making announcements about electric vehicles or talking about the environment or talking about hydrogen now. And the thing that has changed over the past 3 to 5 years is, if I look back, these things happened independently. So there were times when people were very interested in hydrogen. There were times when people were very interested in CO2. There were times when people were very interested in fossil fuels. Now all of them have emphasis at the same time. So it's really critical that many researchers, many companies, all the governments are focused now on solving some very big problems. So it's a great global community. One of the things everyone looks for to help solve it is adsorption. And there's great promise there because adsorption relative to the other methods really starts to take a look at being much more energy efficient and with new materials, the capability of doing new and interesting things. So how does this affect characterization on our side? Because we really focus on characterization and we utilize adsorption all the time to generate information that you all use to discriminate between materials. And one of the really challenging pieces is we've got tools like BET surface area that are quite old, right? You know, these tools now are starting to approach 90 years old, right? 1938 is when people started using BET surface area. And it's been quite useful and valuable across many materials and industries and researchers. So it's a really great tool. And for many years, there were very simple rules about using BET surface area. And one of them was, you know, how do we look at applying BET surface area and actually reporting it and calculating it? So it was a very narrow range. Universally, we would consider that, you know, when we measure adsorption, we would look at relative pressure ranges from about 0.05 to 0.3. So, you know, in absolute pressure terms, we're looking from about the adsorption of nitrogen on the surface from about 35 torr up to about 240 torr of absolute pressure. And this worked quite well for reporting surface area of materials. Now, historically, where it has been great and people have always trusted it and used it is if we have a material that's non-porous or mesoporous. So I've got fairly large size pores, 2 nanometers up to 50 nanometers, or non-porous, BET surface area is very, very effective. And we only need 2 simple rules. We only need to make sure that when we apply the BET equation, it's linear, and that when we look at the intercept and we calculate the BET constant, the BET constant is greater than 0. So 2 very simple rules for applying BET surface area. We start to worry and we start to have difficulties when the material has some microporosity. So if the texture of the material has pores smaller than 2 nanometers, it becomes very challenging to properly apply BET surface area. Okay. It's a really critical application because you see from this material, it's a fluid cracking catalyst. So it's an FCC material. This is the most widely used catalyst in industry. It's used to transform heavy gas oil to gasoline and diesel. So it's a standard in the energy industry for allowing us basically every day to get in our cars and drive to work. It really helps increase the amount of gasoline and diesel available from crude oil and get the correct balance for what people need for transportation. So it's really challenging. It doesn't work so well. These historic rules don't work so well for materials that are microporous and particularly important materials. If we look now at the modern standard for calculating surface area, it is much more challenging to calculate surface area on these materials, but we have tremendous rules now for how to practice BET surface area and calculate surface area so that everyone can do it. And we could get very good, consistent results, regardless of who is calculating that. And beyond that, the rules are so well defined that we can calculate surface area automatically. We need much less user intervention, so you no longer need people to decide this is the correct range for surface area. This came about a little over a decade ago. The researchers at CNRS in Marseille, Roquerol, Llewellyn, and Roquerol, studied microporous materials extensively, and a great driving force for them was the emergence of metal organic frameworks. That with metal organic frameworks, they realized they needed to take much more care in calculating surface area. So they came up with an additional set of rules for calculating surface area. One of them you see graphically in the upper right. You see this plot that looks like a volcano. And from that plot, now we understand that we can automatically select the correct range for calculating surface area. So using a new transform from Roquerol to complement BET. It doesn't replace it. It helps us understand BET more in calculating surface area. So now we could collect the correct range for calculating area. The same rules apply, that it has to be linear. And now there's an additional rule that when you calculate surface area, it cannot be an extrapolation. So when I calculate surface area, the data I use for calculation must envelope where we actually predict the surface area will be from BET. So putting all of these rules together now, we can automatically calculate surface area, which is quite nice. There are some challenges that remain when we look at surface area. And these challenges are becoming more and more apparent with new materials. When we look at materials, materials often have distortions during adsorption. So if we think back to some of the early ideas about BET surface area and measuring surface area in general, we assume the solid doesn't change. We assume it's nice and stable. That's not always true. A very common example of this is the zeolite ZSM5. If you take the zeolite ZSM5 and you synthesize it with only silica, without any alumina present, the structure is actually quite flexible, and it can undergo a phase change during adsorption. The difficult part of that phase change is that phase change gives a second step in the isotherm, so it's more challenging to calculate surface area for materials that have phase changes. Now, the pure silica MFI, this has been well described and synthesized more than 50 years ago. So this problem has been known for quite a while. It's been discussed in various ways, but a little over a decade ago, it was demonstrated that it's actually a phase change. The material is distorting a small amount during adsorption, and the distortion's only about 1%. So a very minor distortion, yet the quantities adsorbed go from 80 cc's per gram to well over 100 cc's per gram. So you can easily see a 30 to 40% increase in adsorption simply from a minor phase change of the material. Okay? So that really has introduced quite a few challenges associated with measuring surface area. There is a wonderful new perspective article that's been published on understanding surface area. And it's really worth reading. It's not very long. It's a short perspective. It was quite a large study globally for looking at surface area. It's available from Advanced Materials, and it's open access, so everyone can go there and easily read it. What David Farian Jimenez and one of his graduate students has reported, and what they discovered was if they take a set of isotherms, so nice adsorption measurements, and send them across the globe to different researchers will report back different surface areas because of their judgment on how to calculate surface area. So when we look at, and you can see this in the center panel, the x-axis, those are all the different materials. The y-axis, that's the range of surface areas that were reported for those materials. So if you look at some common metal organic frameworks like HKUST1, commercially, BASF sells that commercially as C300. We also commonly refer to it as copper BTC. You notice the reporting on that is quite good. The spread of surface areas is actually quite reasonable and small. If you move to the right side and you look at the materials that start with the prefix NU, these are from Northwestern University, and these Northwestern University materials are hierarchical metal organic frameworks. So they have 3 very well-defined pore systems in those materials. You notice that there's very broad range for the reported surface areas. So for all the researchers that received these, they all calculated different surface areas from the same isotherm. Right? You see surface areas as low as 2,000 meters squared per gram to surface areas exceeding almost 9,000 meters squared per gram. And this is one of the concerns now for researchers. There are many new materials, but there are many ways that people interpret BET surface area and the challenges associated with calculating surface area from these materials. So I encourage you all, if you have the time, it's worth reading this article and looking at how challenging it is. There's a great effort now for everyone to try to easily reproduce what other researchers are working on. And these are some of the challenges involved that we've been using BET for nearly 90 years. But as we look at the results that are being reported, how do we know we're all talking the same language and using the same calculations correctly for understanding area? Okay. Material-wise, and this is very significant with respect to metal organic frameworks, zeolites, and carbons now. We are, from the new material perspective, we're seeing more and more materials that may be diffusion limited with respect to characterization techniques. And some of these diffusion limitations are coming into play for things like nitrogen adsorption, particularly on carbons and zeolites. The IUPAC recommendation is to use argon, but you'll see some limitations we have with argon. CO2 has been used very effectively for microporous materials, but there are limitations there. CO2 doesn't necessarily have strong interactions with some chemistries. So CO2 can be very effective for carbon. It may not be quite so effective for non-alkaline exchange zeolites. So typical zeolites that are used for catalysis. And likewise, some MOFs may not be particularly suitable for CO2 adsorption. So there are some surface energy limitations that we all need to be careful about. There's been a trend now to start looking at unifying pore size distributions. So if you have 2 isotherms from different gases, how can we use both of them simultaneously to understand the pore size distribution? Okay. Modeling is now quite extensive for understanding pore size distributions of materials. And one of the areas we particularly like to look at all the time is if I have nitrogen, and you see nitrogen on the top in blue, how dense is the nitrogen in the pore system? So if I'm at a 0.5 nanometer on the left side, you notice the light blue shading. The density of nitrogen at in a 0.5 nanometer pore is less than the density of bulk liquid nitrogen. Okay? And the bulk liquid densities are listed on the right side for you. Likewise, if I do the same for argon or oxygen, we've got the same behavior. So in a typical carbon, the density of these fluids is quite low, below in that 0.5 nanometer range. Okay? Basically, it's a packing effect that you cannot fit that many nitrogens or oxygen or argon into that very small space. Right? If we look at CO2 in black, you see very high densities below a 0.5 nanometer. So CO2 is very, very effective below a 0.5 nanometer. But once we get up above 1.1 or 1.2 nanometers, the density drops off quite quickly. And this is at ice temperature. So CO2 is going to be very effective below 1.1 nanometers for adsorption. And then finally, at the very bottom, you see how effective hydrogen can be in some of the very small pores. So as we approach 0.3 nanometers, we can get quite significant densities of hydrogen in a 0.3 nanometer pore. But as soon as you start approaching 0.5 or 0.6 nanometers, the hydrogen density is quite low. Okay? So exploring the fluid a little bit, and as a function of size of porous materials, modeling can be quite effective. These types of models can be developed with NLDFT, which is quite popular. Could be developed with Monte Carlo type methods as well. If we start to apply these models and we start to think about these problems and how we can use this information to improve characterization, one of the things we immediately see is there are some very challenging materials for adsorption. The C1012 that you see on the right side, you can purchase this from Supelco. So this is really quite a common material that's used extensively for chromatography. So you can easily purchase the C1012. And if we look at the adsorption related to it, the nitrogen you see, and that's the orange line, notice the nitrogen is limited to what can be learned about the material. So below 5 angstroms, a 0.5 nanometer, we really lose resolution with nitrogen. Similarly, if we use CO2, and that's in blue, we don't have much resolution above 10 to 15 angstroms. So we don't get a full range. If we take both isotherms together and model both of them at the same time, not model nitrogen, then not CO2 and paste them together, but actually do a simultaneous modeling, we get a beautiful full-size pore, beautiful full pore size distribution. You see that in green. So the technique now and where the trend is going is to use multiple isotherms and have a consistent approach to looking at pore size distributions. On the left side, you see it for a range of different materials that have different pore size distributions, different treatments to make those carbons. Okay. The fluid density slide from earlier gives us some nice motivation to think about using hydrogen now. Application-wise, it's important, but also from a characterization standpoint. And we learned this about 2 decades ago. We learned this in the early 2000s, that hydrogen was very good for adsorption at 77 Kelvin. And we were doing it mostly from the storage standpoint and the application space. But as we were going through the process, we learned we could use it for characterization as well. So that's been a recent focus in trying to understand materials and understand, can we use hydrogen effectively? So you notice on the right side for CO2, you only see a single isotherm for every size, right? So in red, 3.58 angstroms. But on the left side, when you look at hydrogen, notice there are two for each size. There's a light blue and a dark blue for each size. The light blue is if you assume hydrogen is just a hard sphere. The dark blue is if you take into effect that at 77 Kelvin, hydrogen wobbles a little bit. It has a quantum effect. So hydrogen is effectively slightly larger than we would consider if we just modeled it as a hard sphere. So it's an extra correction we have to consider. Okay, so common material, we look at charcoal, we look at different adsorption on the charcoal, and you notice that if I can easily absorb oxygen on there and get quite good isotherms. Likewise, we can have hydrogen adsorption on there. The difference in the upper row is just scaling. So on the left side, I have a linear scale. On the right side, a semi-log for pressure. And then down below, the pore size distributions. So notice with either oxygen or hydrogen, we get very good pore size distributions. Combining them is not unusual. It doesn't create any strange artifacts. But using a combined method, we do see larger pore volume. And that's what the red arrow is indicating, that when we take two together, we're probing more of the pore system because the hydrogen can go to regions of the charcoal that the oxygen cannot get to. And this is one of the classic diffusion problems and some of the issues we have with understanding materials. Okay. If we change a little bit and we start looking at chars, and char is always very challenging for characterization. Notice things switch a little bit when we look at char. So for example, now hydrogen has the highest amount of adsorption, and you see that on the top, that the hydrogen capacity for this char is greater than the oxygen capacity, the nitrogen, or the CO2. And remember when we looked at the fluid density data, hydrogen only has high density in very small pores. So by comparing simply the quantities, we already know this particular material has a very small entrance to the pore. And hydrogen can get in, it can be very challenging for the others, the nitrogen or the CO2, to enter that pore system. And when we calculate the pore size distribution, notice down below, the use of hydrogen indicates smaller pores than if we were simply using nitrogen or CO2. So the range of gases that are required for full characterization is becoming more challenging. Okay? This effect, again, gets back to being able to use a smaller molecule like hydrogen, and that smaller molecule does give us perhaps a much better picture of the material and the true pore size distribution associated with that material. But again, when we look at it, what's happening in adsorption and characterization, the science behind it is being driven heavily by high quality adsorption data and high quality modeling. The two of them are coming together very nicely. It's parallel to all the other trends we see where having good simulation and good modeling improves our understanding of the experimental data. We can do the same for cylindrical pores. What is really critical about cylindrical pores and worth noting on this particular slide is the densities around 1 nanometer, that there are interesting areas around 1 nanometer where you can get very high densities. When you look to the left side and you see higher densities in that range of about 3 to 4 nanometers, sorry, 0.3 to 0.4 nanometers. Those are challenging areas. It's not so easy to attain adsorption at those sizes, and you'll see why very soon. Okay, I apologize. This slide is quite complicated. It tells a very interesting story, so we'll try to focus on the really interesting pieces of this slide. In each plot, those are the models for different gases. So in the upper left is argon, down below it oxygen, upper right nitrogen, down below it hydrogen. This is how those gases would adsorb in a cylindrical pore. And I have it narrowed, so I'm only showing adsorption in the very small ultra microporous ranges. Okay. As we look at these, we've got to be very conscious of size. So when we perform modeling, we can calculate adsorption that may be in sizes that are ultimately diffusion limited. So we could look at adsorption of oxygen in a pore nearly at 0.34 nanometers, the size of the oxygen molecule. Experimentally, we may not observe that adsorption, and it's a diffusion limitation. Down below with the hydrogen, we really pointed out that there are adsorption in pores with hydrogen. Hydrogen cannot get into those pores because of the size, right? Likewise for nitrogen, upper right, likewise for argon or oxygen. So there are experimental diffusion limitations that we always have to be aware of that can complicate modeling, and it can complicate our interpretation. We also have another issue that we have to worry about. The modeling can give us isotherms, and this is true. This can also occur experimentally, where you can have adsorption in two micropores that are different sizes. And that's this overlapping piece. In the very small pores that are close to the size of argon or nitrogen, you can have adsorption in those pores at the same time that you're having adsorption in a larger pore. It's very difficult to differentiate them if you're only using one gas. Okay? So if I'm only using argon, there may be pores that are 0.35 or 0.36 nanometers that also have similar model pores that are in the 0.4 to 0.5 range. So it's very difficult to decide, do I have which one we're actually modeling and which one we're understanding. When we start to combine techniques and use both hydrogen, a very small molecule, and a larger atom like argon, we can get better differentiation for these very small pores. The main driver for this from in the application space were materials like chabazite. Chabazite over the past decade has become very significant for environmental applications, and particularly diesel exhaust abatement. So using chabazite with copper for the SCR reaction to remove NOx. Okay, so really important to clean up diesel emissions. Chabazite is the ideal material, and chabazite is ideal because it allows researchers to precisely locate copper inside of that chabazite structure, and the location of the copper is really critical for that reaction of NOx to basically nitrogen, so that we're not eliminating some of these really nasty acid gases into the environment, which diesel is known for. So chabazite was really our motivation to look at better characterization in the ultra micropore range. And as you're looking at it, you could see that we got very good adsorption of oxygen and very good adsorption of hydrogen in the chabazite. The left side and the right side, you're seeing the same isotherms, but again, it's a scaling. So the left side is a linear scaling for pressure. The right side is a logarithmic scaling for pressure in those. And modeling them is quite good. And we can very effectively do the same for zeolite 5A. We pick 5A because, again, it's in that size range that is very difficult for nitrogen adsorption. It's just out of reach for nitrogen. So if you start looking at if you start with 13X, you'll get very good nitrogen adsorption. If you move to 5A, it's very difficult. If you move to 4A, it's impossible to get nitrogen adsorption. So we started looking at different molecules, oxygen being a bit smaller, hydrogen, of course, being the smallest, and argon, because that's always the recommendation if it's usable for it. Okay. When we calculate the pore size distributions with these different molecules, and again, we're using two simultaneously. We don't use a single gas anymore. We want to use two because we've established that technique gives us the highest resolution. We see that either hydrogen and oxygen or hydrogen and argon give us the best results, and we can get resolution down to 4 angstroms now. So very effective for looking at different materials and getting the highest possible resolution by combining things. So materials are clearly driving us. The behavior of these materials and diffusion limitations are changing the way we think about characterization and the materials that many people synthesize and what we can learn from them. And understanding the fluid properties and the modeling are all really key right now, that we really can't move forward unless we have very, very good modeling. Okay, one area that remains great potential for everyone for modifying materials is if you start with a microporous material, can we introduce porosity, and specifically meso and macro porosity, to improve the transport properties of the material? While microporous materials are wonderful for size selectivity, catalysis, separations, where they suffer is rate. Because those pores are so small, when it comes to the practical application, they are rate limited. And one way to improve the rate associated with them is to try to change the porosity and really gave great effort and ideas associated with making the materials hierarchical. So having micro, meso, and macro porosity in materials. The challenge we encountered with it is single pressures typically define pore sizes. So this makes full understanding quite challenging of the different materials. And as you view this slide, it's very clear. In the upper left, that's BJH, so that's classic mesoporosity. Notice everything is just single pressure. HK for micropores, same behavior. HK is very specific to slit-shaped pores. Down below, Sato Foley for cylindrical pores, and even mercury pore symmetry. The Washburn equation is very specific. One pressure is associated uniquely with each size. How does that impact the implementation or usage of these models? Well, the Washburn equation, basically when you're looking at liquid intrusion, mercury intrusion, when you get to a specific pore size, the pore completely fills. So you have these step-like filling behavior. With BJH, and that's in the center, you see somewhat realistic isotherm behavior. So you see the nice curving isotherm with a knee, but then when you get to the specific pressure, it's another step change for filling. And then the modern technology on the right side, NLDFT or Monte Carlo type models, those look like realistic isotherms. So 3 really differences associated with it. Notice on the right side, each isotherm does have some different behavior associated with it. And modern techniques, especially when you look at the pore being saturated. So look at the highest pressures from NLDFT. Notice different sizes have different quantities adsorbed. Compare that to the center BJH. Notice it doesn't matter what size you look at for BJH, they all go to the same quantity in the pore. That's the liquid density. Okay, so NLDFT, more precise, more realistic with the quantity in the pore versus using some of the classic techniques. Okay, so looking at these hierarchical materials, and the picture on the left side is a good image of a hierarchical material and how complex they are. That you've got zeolite crystals, you've got some binder material, so something to help maintain the shape. And then within that, there are macropores, mesopores, and micropores. And from the characterization standpoint, it's challenging because I can use mercury pore symmetry for the larger pores, the meso and macropores, and I can use gas adsorption for the micro and mesopores, but how do I put them together? And that's really the critical idea of how do we assemble the data so that, again, we get to a single pore size distribution. Remember, with intrusion, we're always going from larger pores to smaller pores. With adsorption, we're filling from the small to the large. How do we bring the two together now and unify the pore size distributions so that at the end we've got one coherent understanding of the material? On the left side, you see the effects for different zeolites. So the bottom row is adsorption. The middle row is, if we look at intrusion, and notice the difference between the bottom row and the middle row, that in adsorption, I could see small pores and mesopores quite clearly. In intrusion, I could see mesopores and macropores. When I unify them, when I solve for a single pore size distribution simultaneously using mercury data and gas adsorption data, we see the true trimodal distribution and increased pore volume. So pore volume is more precise if I can unify all of the data. If I treat all of the data as being complementary and not being unique, right? The gas adsorption data complements the mercury pore symmetry. We get this very nice result. Okay. There are challenges associated with these different materials and how they behave. And one of them is, and I apologize, my simulation isn't behaving so properly. One of them is small pores can have a dramatic influence on the behavior of the isotherm. Okay, and where you may see this, and you see this quite clearly in hierarchical materials, is you can get different hysteresis loops for different materials. So the material on the left, that set of material, the hierarchical pores, the mesopores and macropores that were introduced were created by protecting the micropores. So it's a demetallation process, some steaming and some treatment with a basic material to etch away the alumina with the acid and steaming, and then the silica with the basic material to introduce mesoporosity. Notice by one set of treatments, we get a very narrow hysteresis loop on the left. By a different set of treatments, we get a very broad hysteresis loop on the right side. If we look at the change in pore size distribution as a function of pressure, we can start to now calculate and understand what is controlling the pore. So on the left side, you see very nicely this pore size distribution. The x-axis is the opening, so the window. The y-axis is the larger pore. So if I have a small window leading to a larger pore, you'll see that relationship. So notice they're all lying on a line of 1. So basically the window and the pore are approximately the same size. So they really look like cylindrical pores. And that's the message from what's happening on the left side. Via a different treatment, notice the porosity in the window is very small, but the pores are quite large. That's a good indicator that we've got sort of an ink bottle shape, that I've got a very small opening leading to a very large pore. So by using these techniques of using multiple isotherms and this scanning technique where we partially fill the pore structure and then empty it and calculate pore size distributions for all of these different hysteresis loops, we're starting to gain some insight with respect to the connectivity in the pore. So do I have a small window connecting to a large pore, or do I have the window and the pore being approximately the same size? We've done similar types of studies with phagosite. So again, commercially, the most significant material, catalytic material that's used globally, and we see the same type of behavior, that by using various forms of treatment, you can create different types of porosity in the materials. What's very nice about this is when we look at images in the lower left, the images agree quite nicely with what we're now modeling and calculating for pore size distributions. Okay. The application space is perhaps becoming the most significant and the most interesting now. That as we look at the application space, CO2 capture and valorization are critical. Hydrogen applications are, again, growing. I'll focus a little bit more on CO2 now and CO2 applications. Where things are changing dramatically in adsorption, and what we see is the use of breakthrough analysis and breakthrough experiments has absolutely become commonplace. So many presentations and papers are being published on this and presented all the time. And the benefit now of breakthrough, and the reason we are so interested in breakthrough, is we want to be able to use multi-components for the gas feed. So having CO2 adsorption or hydrogen or oxygen or argon is very nice for understanding texture. But when we get to the application space, we want to know how do these materials truly perform? What's the impact of water on my application, on my material, and the performance, and where we go with research? Can we do things that are very similar to the process conditions that we're actually going to encounter? That's one of the benefits of using breakthrough. We see it extensively. As you look at the application space, these are the challenges. Whenever we deal with natural gas, you've got this broad range of components in natural gas. So if I just look at CO2 data or methane adsorption data, it's not sufficient. I've got to start considering everything else that's in natural gas. If we look at chemical applications, and particularly regions where there are current processes that are very energy intensive, and where things can be improved, separating ethylene from ethane is absolutely critical, right? Ethylene is a high value feedstock for making polyethylene, which we use so extensively across the globe. So purifying polyethylene and saving money doing it, and hopefully through adsorption, has significant energy impact. So we'll produce less CO2 and potentially use less energy. So there are great environmental benefits, and likewise great economic benefits for doing it. Likewise, we need to be careful and capture CO2. We need to remove this from the atmosphere. Our usage of energy is really driving those CO2 levels to very high and dangerous values, and we've got to be careful. When we think about these projects, we all have to keep in mind These are long-term projects, and it's acknowledged now that they're long-term projects. People talk about these and being successful in terms of where we'll be in 2030, where we'll be in 2040, where will we be in 2050. Okay. So as we look at breakthrough, there are really three interesting pieces of the breakthrough experiment. We're simply flowing gas, and we can flow a mixture, and then we're going to monitor what basically elutes off of the sample. So at the inlet, I could have water and CO2, and then I want to know, when does the water come through? When does the CO2 start to break through? So how much of each is going to be absorbed? Is one preferentially absorbed versus the other? If we don't have any signal, you see that that's typically complete adsorption, versus if we start getting to a region where concentration is increasing in the green in the center, that's typically breakthrough. And then when we get to the final stage, all the way on the right side, the material is completely saturated, so it has a stable concentration on the surface. So conceptually, the breakthrough experiment is quite simple. We're going to flow gas where we know the concentration. We're going to monitor the concentration as it comes off of the sample. Okay. We typically use a non-adsorbing gas in the mix. And the non-adsorbing gas is used in the mix because that helps us understand just simple flow through the sample bed, right? That basically tells us, well, I started flowing helium and I started flowing CO2 at the same time. When do I see helium? When do I see CO2? The difference between the two, very nicely, is the quantity adsorbed, and that's what's in red. Okay. So if we look at a really typical application, and this seems to be now the standard for breakthrough, and especially with CO2, people will show you 13x zeolite with CO2 adsorption. They'll typically run multiple cycles, and we can calculate the quantity of CO2 adsorbed. You see that on the right side for different cycles. This is a nice piece of breakthrough because you can program the device, or you could program your breakthrough experiments to run multiple cycles and watch the performance of the material. Does the material degrade? So this is really simple, just CO2 and the zeolite. We can change material, right? So you look at zeolite 5A, and you get quite a bit more adsorption, but the capacity changes rapidly. So the first cycle has the highest quantity absorbed. Second and third cycle see some degradation, so you're not getting quite the same capacity you had. Metal organic frameworks, very good performance, very consistent. The difference compared to the zeolites, capacity is lower. Okay, very consistent, so very robust, but overall lower capacity. And then likewise, we change metal organic framework, look at an iron BTC. Again, we see the same type of consistency as we did with the mill 53, but a little bit more gradual, so we see some mass transfer limitations. The shape of the curve can be quite valuable. When we overlay all three of them, you see the performance there, that the 5A zeolite has some of the best initial performance. The 13X perhaps quite similar for robustness, and the mill 53 quite less capacity, but very robust and stable over the. With CO2 capture, one area that people have been quite interested in is, if I have a solid, can I enhance the performance? And one way is to take an amine and support that amine on the solid. Amines are quite effective for CO2 capture. They've been used in the liquid phase for many decades industrially for CO2 scrubbing. So amine technology is quite well developed, but now if we combine it and put it on a porous material, how can we use it? Right. So here's the nice benefit of now looking at breakthrough. We can use water in the mix, right? So using breakthrough type of analysis in these dynamic experiments, we've got to be more careful. Water adsorption and equilibration tends to be quite slow. So as we go down this path of looking at water, one of the typical behaviors and practices we should use is we should make sure the sample is equilibrated with water first, because that's going to be really a big driving force in precision. Then in blue, you see the helium tracer gas, and then finally on the far right, you see the CO2 breakthrough. So we can calculate the CO2 adsorption in the presence of 40% relative humidity. So notice on just the simple silica aluminum material, there's very little CO2 absorbed, 0.028 millimoles per gram. If you take that same material and then use it with the amine, right? So with amine loaded, we can increase the capacity, right? We have effectively tripled the capacity of the material just by using the amine rather than the pure silica aluminum. If we change the type of amine, right? So we go to a different amine, much more significant adsorption can be obtained in that same 40% relative humidity stream. So, now we're looking at an improvement of effectively 8x. So, by adding the simple amine, we could triple it. By adding by changing the amine, we can now go 8x. And you notice the performance now starts to be very similar to the microporous materials, but in the presence of water. So really significant now that we can do the multi-component analysis and start to truly understand materials and gain better insight into the materials. Okay? So breakthrough has become quite significant and maybe perhaps one of the most popular tools right now for researchers and likewise for development on the engineering side of things, because multi-component data is available. It does allow us to look at process conditions. It does allow us to use things like water. So we can really focus on having realistic feed streams and understanding potentially everything that is going to go on in the system, and allows for use in many, many applications. Okay. A few acknowledgments here. It's really important. None of us really do all of the work anymore. Really significant piece is who we collaborate with. So I've got some great collaborators over the years. The NLDFT modeling was performed by my good colleague and close friend here at Micromeritics, Jacek Jagiello, who's been active in this area for many decades. The breakthrough analyses were done here by a new colleague, Julian Hungerford. Julian is a young PhD who really is an expert with breakthrough and has been using it now for quite a few years, and understands all of the mistakes that you can make with breakthrough and helping us all make sure we don't make those mistakes. And then, of course, Sharon Mitchell and Javier Perez Ramirez. I've had the unique opportunity to collaborate with them for about a decade. All the wonderful zeolites and hierarchical zeolites, those were collaborative efforts with the materials that they were able to provide. So thank you all. It's always a pleasure to talk about adsorption. We love this topic. It's a topic that keeps getting more and more interesting. The characterization piece continues to be challenging. I think we're all making great strides in the real application of these materials. We're getting closer to having phenomenal tools like Breakthrough for providing greater insights to everyone that uses adsorption so importantly for their research. So thank you all. I'm happy to answer any questions.
Thank you so much, Professor. I'm trying to activate my camera. I don't know if you can see me. Thank you so much. I was actually surprised by how much error all the researchers around the globe can have when calculating something as simple as the surface area And let's not talk about how much error we can have during pore size distribution, right? just surface area, which is something like, as you said, it's almost 100 years old.
Yeah.
And I'm just wondering, when then maybe we as researchers and also as reviewers of other people's work, what should be like demand that the people actually report when doing the calculations in order that we can actually trust a value? That's one. And the other one is like how we can actually be certain of a result as high as 9,000 square meters per gram during the calculation.
Yeah, really a wonderful, a wonderful question, and this is a great. It is a current focus of so many people that they are absolutely concerned about what is happening there and the variability of what's being reported. Because again, this is everyone had the same data, so no one had to make measurements. This was clearly sharing it, and what we discovered from the process was that even though the rules that we all used apparently were the same, there were many different ways that people calculated it and their considerations for the calculation. So a few things that came out of this is that the raw data, the actual adsorption data, should always be reported. And, you know, if whenever it's possible, if you can include that in your supplementary information, that is really critical. It doesn't really need to be perhaps in the main manuscript because we all understand that, you know, you may be calculating BET from nitrogen, but if you put that in the supplementary data, then people can compare their experimental data and understand that what they're measuring matches your adsorption isotherm. Another piece that came out of some of these discussions and may not, it doesn't necessarily show up in this perspective piece, but it was discussed extensively at a Gordon conference in 2019 was we had multiple discussions on the fact that when you synthesize a material today, your material may be better than the original material that was synthesized. So for example, HKUST1, the current level of synthesis is far better than it was when the material was first reported. Because of that, surface areas for HKUST1, if you look at the different papers over time, the adsorption data is better. It has higher surface area, it has higher pore capacity. So again, if people will report someplace that it can be seen, the original adsorption isotherm data, it's great to see that. And then they can directly calculate surface area and understand things have changed. There's been an improvement, or perhaps their synthesis isn't as good. I think everyone understands, and again, put in the supplementary information and report what range you calculate, what range of data were used for calculating BET surface area very simply. And did you use any specific considerations associated with it? The calculations and reporting become more challenging on these materials, and you see it in orange on the left side. Notice there are multiple subtle steps in that isotherm. So the data that is the worst, the NU1104, that is the worst. That was the most difficult. That has the most steps in the isotherm, and there are 3 clear subtle steps in that isotherm. So it's challenging, but it seems to be a consensus that having the original data in supplementary information in papers will help resolve some of this problem, and more reporting of it so that there's we all understand what the original data was used, and then some brief comments in that area on how it was calculated.
And When calculating pore size distribution, do you recommend that also people should add the fittings to the equations they're actually using? Because I have seen a lot of papers they use no local DFT, wherever, and they just report a pore size distribution. They never mention that the equation they actually select it was correct. What do you recommend in this field?
So reporting the fit. Reporting the fit is really critical, and particularly with gases like argon, nitrogen, oxygen. Wherever the fluid where you can actually get to complete saturation and condensation tends to be really critical. And the reason and the place where it's critical is when you report the fit, and the best way would be, as you're looking at this slide in the upper right corner, you don't want to see any unusual wiggles in the fit. So you really want to see a good representation of the original isotherm. So here, when you look at the red line that's going through the data points, it's a reasonably good approximation. You don't want to see unusual behavior in the fit. Unusual behavior with the fit will create gaps in the pore size distribution. And that was quite common early on with NLDFT, that for many materials, people would be reporting a pore size distribution, and there would be a gap and some absence of pores, and typically that was around 1 nanometer. So reporting the fit is absolutely critical. Again, it's someplace that it doesn't necessarily shouldn't be in the main body of a paper, but it will be quite valuable in the supplementary information, that then people can go back and really understand, oh yes, your modeling was quite good, and we can trust the pore size distribution. Because when we see that unusual fit, we're all quite concerned. Is it a software problem? Is it a model problem? Is it experimental data problem?
Yeah, because sometimes we see like a pore size distribution that is too sharp, or that it has almost no pores at 10 Armstrongs or 20 Armstrongs, which is, I think, something related with actually the calculation. So one can um one can I don't know, guess that there is something wrong with the calculation, but we're never sure because we never actually see the fittings.
Yes, and the two sizes that you discuss, um, the 10 angstrom is very typical on carbon, and the 20 will be a bit more typical for cylindrical pores that you may see an absence in those locations. Um, it From the model standpoint and the calculation standpoint, if the model is not handling things properly at the same sort of isotherm range as 10 nanometers on carbons, that's a 10 nanometer pore, or sorry, 10 angstrom pore and a flat surface can appear to be the same. So the calculation, basically not the model isotherms, but actually the calculation process has difficulty differentiating between a pore size and a flat surface, for some of the older original models. The more modern models, that's properly taken into consideration. It's the same effect for cylindrical pores, and that occurs at 20 angstroms. So yeah, your comments about the strange absence, we've seen exactly the same. And when we've looked at it over the years, it gets back a little bit to the way you go from experimental data to pore size distribution and what's inside the model, for it. And it always gets back to older models where everyone assumed that the pores were homogeneous, that there wasn't any heterogeneity on the surface. Once we started introducing heterogeneity about a decade ago, this problem has become less severe.
Okay. And we have some questions from the chat. Gamaliel asked, for practical applications, adsorbent catalysts are used at millimeter-sized particles instead of very fine particles of micrometer size. Indeed, diffusion limitations are important at millimeter-sized particles. On your opinion, pore size distribution and BAT areas at millimeter-sized particles can be obtained with the same certainty that very fine particles?
So yes, so you can obtain very good pore size distribution data on both. As the particle gets bigger and you get to these practical sizes you're talking about, um, things you want to explore and be more careful about is how long it takes to make the measurement, and be a little bit more cautious about the timing, so that it may take longer for equilibration for larger sizes when they're extrudates or pellets. The additional time is because it's more difficult to remove the heat. So if I've got a fine powder in contact with a very cold surface, I can easily remove the heat during adsorption, and the heat tends to really slow down adsorption. When it gets to a larger size, we don't have the same good contact with the glass like you typically would during a measurement. So it takes a little bit longer to remove the heat. Even with fine powders, if you use a very large bed and it sits in sort of a pile, it will slow down the equilibrium. So that's one consideration, that you just perhaps a bit more patience associated with how long to conduct the experiment. The second one that goes along with it is, of course, when you make these materials, you could have very significant tortuous paths, and you could have occlusions. So, looking at the pore size distribution of a formed material from the powder, they may not overlap as well because of you could have quite a few occluded pores. You're definitely going to create some new pores. Naturally, you're going to introduce a lot of macro porosity that you may not see in the powder. So, and adsorption in those macro pores is quite fast. So there won't be any serious concerns about that. But yeah, there's definitely going to be a new pore structure because of the way the particles are put together. And again, it's strictly a bit more patience and making sure the sample is fully equilibrated. It is much more difficult to measure a pore size distribution on something like a pelleted zeolite than a powdered zeolite.
Okay.
It's much more challenging. It takes much more time. If you start off with 13x pellets, it could be 5 to 6 days to get a high resolution isotherm. If you powder it, it's on the order of 2 to 3 days or less. So
Okay.
again, it's removing the heat can be challenging, and also you will get into some diffusion limitations. But going from the outside of a particle to the inside of a particle with the gas phase is on the order of seconds. So it's not, the diffusion limitations really then get back again to the micropore size of things. Removing the heat becomes very challenging.
Very good. Norma Tiempo Flores is asking, what are the recommendations regarding flexible metal organic frameworks for the analysis of surface area and pore size distributions?
I think for MOFs, particularly with surface area, the bare minimum is if you can measure with nitrogen, and in general, nitrogen seems to be quite effective for it. Measure BET surface area, measure a full pore size distribution as well. And when you calculate BET surface area, you want to use all of the rules that were introduced from Roquerol. We have a benefit in our software. It's built in. There is an add-in component you could put in that will scan your entire isotherm and calculate the appropriate PET surface area. It coincides really well with the article from David at Cambridge. So, you know, if you have our software and you can get it, and with any isotherm data, you can use it, it will calculate the correct surface area to agree with what's being published. It is more challenging. I would use nitrogen. On the pore size distribution, the general trend has been to use the same type of characterization you would use for zeolites. So people have practiced quite a bit using, you know, if you want to use classical methods, using Sato-Foley for calculating the micropore size distribution. If you're using NLDFT or Monte Carlo, you want to use oxide surfaces. The surface energies seem to be similar and give reasonable results. We do have a MOF-specific model for pore size distributions, and I'm happy to say that particular model was developed around the really difficult to characterize MOFs. These Northwestern University series was really challenging, and we were able to develop a MOF-specific model really to coincide with those challenging materials. So you'll see more in the future. You'll definitely see more models for MOFs, but right now the general trend is use what you would use for a zeolite. If you want to be more specific, we do have a MOF-specific model available. For pore size distributions on the MOFs, it's probably best to use argon. The analysis time will be shorter. The quality of the adsorption data will be quite high. It's much easier to work with the argon. For surface area, unfortunately, we all use nitrogen for surface area. It's the most widely reported. So that's going to be a nitrogen experiment. Nitrogen versus argon for surface area. People would love to use argon. It has been suggested. The challenging piece of it is, from a literature standpoint, we don't have agreement on, you know, for example, what's the size of an argon molecule on the surface versus nitrogen, where we all agree to use a specific value. So it makes it very easy to interpret nitrogen surface area data. We all know we're using the same parameters or the same properties for nitrogen. That's not quite the case yet for argon.
Very good. And my last question is, I don't know if you could tell us a little bit about the most recent instrument or models or advancements that Micromeritics is doing in terms of characterization of porous materials.
So on in two areas on adsorption, we are really very focused. One is we want to bring to everyone the ability on the single component adsorption, so static adsorption, the ability to use whatever gas or vapor you want to use, because the application space there is okay. We all use nitrogen, argon, krypton for characterization, but I want to know if my material adsorbs nitric oxide, or I want to know if my material adsorbs ethylene. So we're continually focusing there to make sure we've got the correct library for you to make those measurements. And that's basically the device we call the 3-flex for adsorption. We continue to develop that to monitor, to make sure the hardware we have is the best we can put in there, but likewise the tool set that you use. So, you know, if you want to use ethylene, you can just go there and use ethylene. You don't have to go searching for information on how to use it. So that library keeps changing. We're increasing the modeling capabilities inside of our software. So some of the common things that are used for multi-component, where there is a read across to single component, like IAST, predicting behavior, predicting adsorption isotherms and equilibrium. That's coming in our next release of software, as well as better tools for calculating heat of adsorption. So once you have data, make it much better so people understand how heterogeneous their surface is. So improving the ability to use more vapors, improving capabilities and making it easy to calculate things like ideal adsorbed solution theory in a standard way. Likewise, better ways to calculate heat of adsorption for isotherms. On the multi-component side, we've got the breakthrough analyzer where we've combined what we know about chemisorption because chemisorption can be in many ways so much more challenging than physisorption because the quantities are quite small. We've got to be very careful about flow details for chemisorption. So we've taken our knowledge there and applied it with some new patents for breakthrough. And we believe that our breakthrough analyzer is going to really help researchers that make small quantities of material that want to understand performance, the application performance of their materials. So the breakthrough analyzer is the latest introduction that was earlier this year in January. On the chemisorption side, we've just introduced an updated chemisorption analyzer that we think is further gives you more capabilities than ever before. It allows you to do, in addition to typical characterization, now you can do temperature programmed surface reactions and flow vapors, which is in typical chemisorption style, people have always had the ability to pulse a vapor, but flowing a vapor is quite interesting because you can do more reactions and you can also speed up the analysis of the performance. So we love adsorption. We love working on these instruments. We have a little bit of a benefit. We get to play with these new instruments 1 or 2 years before you get to see them. So we're always excited about working on new ones. It's really nice to see all the publications you all have made with our instruments. And if you ever need help, I've got a great group of engineers and chemists and physicists. Please reach out to us for help.
Thank you so much.
Javier, if I can make a quick comment.
Of course.
I'm very proud of the team that we have at Micromeritics, and one of the examples is the knowledge that Jeff is willing to share with the audience. But as he mentioned, we are loaded with talent and knowledge that we are always very willing to share with whoever wants to learn or put a little challenge on interpretation for better results. So we are an interesting group of people at Micromeritics. We are developing our own technology. We did not acquire others and then try to do something with it. We are developing our technology. And that's a great asset for presentations like this, that we can give a review of a little bit of history, a little bit of the errors that exist, how to fix them, and where we are going to make these tools a lot friendlier to the user so that we can get good results. So thank you for allowing me to bring to you, to AMDA, Dr. Jeff Kenvin, because I'm just proud to be able to introduce him to you.
I'd like to, and likewise, I'd like to say thank you. Again, I said that, these are, it's a wonderful opportunity to talk about things you love. And that's why we all do this, right? That's why you all are interested in adsorption, because we love this topic and we love how it can be used. So it's a great opportunity, and it's really wonderful to have questions to talk about how to make things better and how we can all go forward and improve. So thank you all. I'm really looking forward to your first in-person meeting. So please let us know when you have your first in-person meeting, because it's nice to do things virtually, but it's nice to be with people and sometimes have lunch and discuss adsorption.
Absolutely. Of course. Thank you very much, Dr. Abel, Dr. Jeff. And I'd like to I'm gonna share my screen so I can share the recognize to Dr. Jeffrey Kenvin from the Mexican Association of Adsorption. La Asociación Mexicana de Adsorción le otorga el presente reconocimiento al Dr. Jeffrey Kenvin por haber impartido la conferencia Current Tendencies on Adsorption in Global Markets today, and is signed by our President, Dr. Nancy, and our Secretary, Dr. Jacob, which was also in the audience. And well, I'm gonna change to Spanish for all our audience. Muchas gracias por haber estado con nosotros. Le agradecemos al personal de Micromeritics, los doctores Abel y Jeff, por haber estado en la conferencia. Y también, desde luego, a nuestro patrocinador en Nanociencias, pues, por habernos dado la oportunidad, la facilidad de traer esta plática a nosotros, ¿no? Y que, al menos en lo personal, fue muy académica, aprendí muchas cosas que no sabía. Espero que lo haya sido para todos. Thank you so much again, Dr. Jeff, Dr. Abel, and we're looking forward also to your new instruments, your new models, right? We're also hoping to get some grants for buying new instruments, of course, all the time. And thank you so much again. I hope we can meet soon in a personal conference.
Thank you.
Thank you.
Same. Thank you very much. Have a great weekend.
Have a great one. Gracias a todos y nos vemos en nuestra siguiente ponencia, el doctor Roberto Muñiz, el día 8 de julio. Por favor, manténganse al pendiente de nuestros correos, de nuestro newsletter. Y les comentaba que también tenemos un detallito con la emisión de certificados de esta ponencia. Por favor, no pierdan la paciencia, les va a llegar un poquito tarde, pero les llegará. Y bueno, nos vemos. Hasta luego. Bye, bye.
Hasta luego. Gracias a todos.